So in this video, we're going to look at working with Taylor polynomials. Once we've generated them and come up with general formulas, what can we do with them now that we have them? Now, for many of these functions, we're simply going to look up the standard functions in the table because we're going to work with Taylor polynomials centered at common points like 0, so the Maclaurin series. But these techniques apply to any Taylor polynomial centered at any point once you've generated it. Now, suppose that we want to create a power series for the function e to the negative x squared. Well, we can do that if we want to actually go through the formulas and take our derivatives and everything else, but sort of the standard way. The problem with that is, of course, as soon as you take this derivative of e to the negative x squared, you get a product rule with a chain rule, and every single time your function gets more and more and more complex. And so it becomes very difficult to actually do all of those multiple derivatives and then generate a general formula from it. But what we can do is we can actually take our e to the x function and substitute negative x squared everywhere we had an x. And that will generate our Taylor series, our Maclaurin series in this case, for us. So everywhere I have an x, I'm going to replace that with negative x squared. And that's going to give me that negative is being raised to the n power. So that's my negative 1 to the n. And then x squared is being also raised to the n power. So that's my x to the 2n. Now, this function is very important, particularly in statistics. It represents the normal curve, or the slight modification of this represents the normal curve in statistics. And so when we want to do calculations of probabilities, it's a problem that we can't actually integrate e to the negative x squared by itself. And so we can use the Taylor series to generate our best approximation for as many terms as we like by simply integrating this Taylor series. And because this is a sum and we know that we can take separate terms in our integral and integrate them separately, we can just integrate the function, the expression for each of the terms in our series by integrating the formula. And so that's just a power rule because there's only one x here. And so we add 1 to the exponent, divide by the new exponent, and we get a function that we can use as summation where we can approximate this antiderivative to as many terms as we like with as much accuracy as we desire. Now, another example that we can do is we can use a power series to evaluate limits. So we know from Calc 1 and from working with L'Hopital's rule, we had different ways of confirming that the limit of sine x over x is equal to 1. So we could do this numerically. We did this using L'Hopital's rule, but we can also use Maclaurin series to do this. Since this is centered at 0, we have our formula for the sine function. And then what we can do is we can simply take that formula and divide by x. And if you divide this formula by x, basically you just drop off this plus 1 in the exponent. So this becomes x to the 2n. And then the power series for this function can then be written out this way. So again, this was x to the 2n plus 1 divided by x, which gives us x to the 2n. And we generate the terms by plugging into the formula. And then when we take the limit of this expression as x goes to 0, all these higher order terms disappear and we're left with just 1. And then we have some additional ways that we can also work with these. We can also multiply them, and we can actually do long division. The example we did with the limit involved only dividing by x, but you can divide by just polynomials as well. Now, the trick with dividing by polynomials, so if we were estimating, let's say, x plus 1 instead of just x, When you're doing the long division, start with the constants for both the Taylor series and the thing that you're dividing by. It's a little bit backward of what we did when we learned how to do this before, but the powers for the Taylor series will go on forever. So there's no place to start with the highest power. Instead, it's the higher powers that we're going to drop off and keep the lower degree terms. So you'll just have to flip everything, start with your constants for both the thing you're dividing by and the thing you're dividing into, and then follow the general procedures, the same procedures you did with regular long division. Now for multiplication, you do have to be a little bit careful about this because there is a sort of a desire to like get to the end quickly. And sometimes that will induce people to think, oh, I can just multiply this formula by that formula and then I'm good. But that's not how multiplication works. We have to FOIL. So if I want to create a Taylor series for, let's say, sine x, cosine x, then what I have to do is I have to FOIL when I multiply the first couple of terms for sine x and the first couple of terms for cosine x. Now, it's asking me for a polynomial of up to degree 8. Okay, so I generate my terms for the sine x and the cosine x up to that point, and then I FOIL them just like I would with a regular polynomial. So I take my x and I multiply it by these terms. Now, because I'm telling myself I only need to go to degree 8, when I get a term that's going to give me degree 9, I can quit. So here I'm going to multiply x by 1, and then x by x squared, that's x cubed. X by x to the 4th is x to the 5th. X by x to the 6th is x to the 7th. But if I multiply x by x to the 8th, I get x to the 9th, and I don't need it for this estimation. So I'm really only multiplying x by these first 4 terms. When I go up to my x cubed term and I start FOILing that, well, x cubed times 1 is x cubed. That's still under degree 8. X cubed by x squared, that's x to the 5th. That's still good. X cubed times x to the 4th is x to the 7th. But if I multiply x cubed by x to the 8th, I'm definitely, or even x to the 6th, I'm getting x to the 9th. I don't need it. So I'm just multiplying x cubed by the first 3 terms. The rest of them, I mean, they're there, obviously. But since I said I only wanted to go to degree 8, I don't care what the x to the 9th term looks like. And so this will continue each time. You will multiply by fewer and fewer values until you've exhausted all of the terms, in this case, in the sine polynomial. And then you will, when you actually do the FOILing, you will then add up the like terms. So this x multiplication produced 1x, and that's the only x. But then I got an x cubed from here and from here. So this x cubed and this x cubed get added up, and then continue on adding up the results of our FOILing. Now, sine x, cosine x is equivalent to 1/2 sine 2x. And so there is another way that I can generate this polynomial or verify my results, and that is by using this identity and then doing the calculation that way, as we did with the substituting negative x squared into the exponential function. I can take my sine expression and substitute in 2x and then divide the whole thing by 2. And what I should get is all of these terms are the same, if I've done my math correctly. So often generating these functions, there's more than one way to go about them. You do not have to brute force them every single time.